All right, well, good evening and welcome to lecture 14 for MT225. Tonight we're officially starting into our second third of the course. In the first third, we learned the basic principles that we need to do structural analysis. We learned about forces and vectors and equilibrium and how to solve for unknown quantities. In the second third of the course, we're going to apply those skills to analyzing relatively complex structures, what we call the truss. Now, last week, I introduced trusses back on Monday night in lecture 12. And if you haven't gotten a chance to see that yet, I would advise you to go back and look at that lecture first. So I'll do a brief review of what we looked at on Monday night, but you'll get a more thorough coverage of it from lecture 12. So tonight we'll be taking a look at truss analysis. We'll review the external problem and figure out how to expose the internal forces in the truss. First, exam one has been returned. I returned that on Saturday, so everyone should have gotten a copy of their results. I do have the physical copies for you, and if you haven't gotten that back already, I'll be giving that to you when I get a chance. I don't want to hold on to more paper than I have to. Those are yours to keep. As far as comments on the exam, for the most part, it went well for pretty much everyone. There were a few missteps here and there, but for the most part, the basic skills were there. The problem 4 was a little bit of a challenge for a lot of people, but don't. The biggest issue there is seeing something that looks very different from problems that we've solved so far. Just because it looks different doesn't mean we can't use the same techniques that we've used before. So just take a step back, think about what kind of problem it is and what's physically going on, and let the analysis follow from that. If you are finding yourself in a situation where you are needing a little bit more in-person assistance with the class, or you're maybe not quite getting the basic skills, take advantage of Tuesday nights. I've had 2 Tuesday night sessions so far, and I've spent them alone. So if you are having some challenges with the course material and want to work out some problems individually, one-on-one, come to the hangar Tuesday night, 4:30, and I'll be up in the upstairs classroom to start with anyway, and I'll stay as long as I need to, but as long as you need me to. So take advantage of that, because we're at a point right now where we still have some time before the drop date. Drop date's in April sometime. You can find it on the academic calendar. And with nobody in the class right now is in a position where they are guaranteed to fail the course at this point. Everyone had performance that was at the very least recoverable. So so if you didn't do so well on the exam and want to do better, let's work some problems out, because you got to have those basic skills in order to go on to the next section. It doesn't get any easier. We rely on those individual skills. So make sure you're feeling comfortable with those. And if you're not, let's fix it so we can move on. Let's see here. So today we're going to review briefly the external problem. So I'll go back over what we talked about on Monday night, but again, there's a much more thorough coverage in lecture 12. So take a closer look at that if you find yourself lost right away. The main meat of the presentation tonight is going to be looking at what we call the method of joints. The method of joints is a method of exposing the internal forces in a truss by looking at the equilibrium of the connection joints, or the pins that hold the truss together. By looking at the forces on those pins, we can figure out what kind of forces there are on the members and what loads each individual member must carry. Method of joints is one of 2 methods that we'll be looking at. In fact, just to give you a heads up, we're about a month away from our next exam. Our next exam is just going to be on structural analysis. It's just going to involve trusses and another structure we'll meet called frames. I usually do 1 week on method of joints. That would be this week. Next week, I'll do the second method, what we call the method of sections. The week after that, we'll look at this second type of structure, what we call a frame. And then usually the week after that, we do mixed bag, pretty much any kind of structure. And we work more on the skills of analyzing structures. And then we go into our exam. So we're in that 3 to 4 week kind of range from our next exam. So bear that in mind. So let's look at truss analysis. So last time I told you that truss analysis is a method of learning everything there is to know about a truss. We look at a truss as a structure that is intended to transfer external loads down to supports. And those loads transfer to the supports through the truss structure, through the members that connect that truss, that form that truss. The members carry a certain amount of load and they have a state to them. They are either in tension, being pulled apart, they're in compression, being squeezed together, or they're unloaded. And when we do truss analysis, we learn two things about each member: how much load it carries and what its state of compression or tension is. So that's our goal. And we can divide that analysis into two major steps. We have what we call the external problem, where we look at the applied loads and we look at the reaction forces from the support and determine what they must be for the truss to be in equilibrium. Now, that may sound a little bit familiar. It's basically the same problem you've been solving with beams on supports. It's the non-concurrent force system. So the external problem is often our first step. Very rarely we can get away without solving the external problem, but life's usually a lot easier if we solve the external problem first. And we've absolutely got to get that external problem right. If we mess it up, then all of our answers downstream are going to be wrong. So we really have to make sure we get that external problem right. Then there's the internal problem. That's what the method of joints that we'll be looking at tonight is designed to solve. The internal problem lets us figure out what the loads are on each of the individual members that make up the truss. So the external problem, that exposes our reaction forces at the supports and gives us more information to work with. The internal problem exposes the loads on the individual members. So last week we looked at the external problem, where we look at the transfer of external loads, applied loads, to the truss supports. So if I go over to the truss that I've sketched on my display, there we go. Here I've got this truss structure, a simple 3-member truss, and this is not all that much different than what you'd find in a lot of houses around here, where you have a span with a joist and then you have a couple of rafters that connect up to form a roof structure. Now the real structure is a little more complex than the truss. If you've done a little bit of construction, you know that they're pretty strict about what goes on in these sections here, how the joist and the rafters connect together. There's all sorts of building code about that, about what happens up here, whether you have ties that go across. So the real structures can be a little more complex, but this gives us a pretty good idea of what's going on. Here, maybe we have 1,000-pound load pushing down right at the peak of the roof. And then we've got, say, a 200-pound side load, a wind load, for example, blowing on the truss. The purpose of the truss is to take those loads that are applied at the apex and transfer them down to the supports. Those supports could be right on the ground. These could be walls. So we're trying to figure out what the support forces must be to keep this truss in equilibrium. To do the external problem, we don't have to care about how these members are connected together or where they're connected. It's essentially one solid piece of material. We could think of it as if somebody just cut a big piece of metal or a piece of wood in this shape and laid it out. That gives us our reactions at the support. That's the external problem. Our system in the external problem is the whole truss. So when we draw our free body diagram, the free body diagram looks something like this. We've got our external applied forces. We've got a pinned support down here, so that'll give us reactions in the Y and the X direction. We'll have a roller here, that'd be our BY. These are points B and A, and maybe C up there. So we get a free body diagram. If we have some geometry on this, we know things like the distance between the supports and the height of the truss. We have enough information to solve a non-concurrent force system. We find our sum of forces in the X and the Y direction. We find our moments about a point. And that'll give us our equilibrium. I'm not going to solve that one here. I'm going to solve one that's going to be a little bit closer to something that we'll be working with here in our example, but that's the basic setup of the external problem. So not too much different than the beam problem. So in the external problem, we ignore the internal structure. It doesn't matter how many members there are and how they're connected together. All that matters is what's happening at the edges, what's happening at the boundary, the external forces. So we look at applied loads and we look at the reactions at the support. And fortunately, we know how to do that problem. That's just a non-concurrent equilibrium problem. Now, the one additional bit of information that we need, or skill or technique that we need in order to solve these types of problems, is there is the one place where this is different than the beam on supports problem is that we've got some vertical height in these types of problems. In a beam problem, we just had something that was very thin compared to its length. So where we had our pin and our roller, it didn't really matter if we had forces to the sides. Those forces didn't have any moments, because if we were pivoting down here, there was a very small arm there, almost zero, so it wasn't worth considering. This could be feet of distance. In a typical roof structure, this would be, if this is 12 feet across, this could be 6 feet up. That'd be a common roof pitch. Or 24 feet across and 6 feet up. That'd be another common pitch to a roof. So the 6 feet is a pretty good arm. Both of these forces up here have a moment about our pivot point A. And so moments we have to be a little more careful about. It's not going to be just the vertical forces that cause moments. The biggest mistake I see people make in solving the external problem is they neglect the moment due to horizontal forces. So on Monday, I went into some more detail on that. I'll just briefly review the technique here, but go back to Monday for some examples. Last Monday, lecture 12, for some examples on how to handle that moment. So we figured out back in early equilibrium problems that we needed the perpendicular component of force times the arm, but we can get the same moment if we use the perpendicular arm times the force. So essentially, we just have to find the distance between the line of action and the pivot point, the minimum distance between the line of action and the pivot point, to find the arm, and that'll give us our moment. So let's look at the picture here. One way to look at it is to think of these force arrows as arrows that are flying through the air along their line of action. If we're picking A here, for example, as our pivot point, the closest that this arrow would ever get to our pivot point would be right here. That distance would be our perpendicular distance. We learned about the principle of transmissibility that said that we could pick up that force and put it anywhere along its line of action, and the physics won't care about where we put it, for the most part, at least for the purpose of calculation. Physically, there are some differences, but for the purpose of calculation of moments, it won't matter. So if we brought that moment down here, that force down here would be a lot easier to figure out. If we knew this distance, we just multiply 1,000 pounds times that distance. That'd be our moment. The same works for our 200-pound force. If I draw the line of action for that, I shoot this arrow through the air, the closest it ever gets is right there, some distance away from the pivot point. and that distance would be the height of the truss. Figuring out the arms for these forces is not usually hard. It's usually something we can read right off the geometry of the truss. We have to make sure we take them into account, though. The biggest mistake, again, that I see people make is they forget about that 200-pound force, the horizontal forces, because they're so used to ignoring them down here in the beam problem that they forget to apply them in the truss problem. But as long as there's a moment, as long as there's an arm, there's going to be a moment. Unless the line of action goes right through the pivot point, there will be a moment there. So let's take a look at an example here. So here's a similar example to the one I've been kind of sketching out, and we did work out the external problem last time on this one on Monday night, but I'll go ahead and work it out again just for convenience here. So there's the picture. I'm going to draw the free body diagram, then I'll switch the camera over. But the free body diagram is going to look substantially similar. We've got 3-member truss with 3 joints to it. The joints are what are labeled A, B, and C. We have a 5-kip force to the right. We're dealing with a vertical force of 10 kips. The height of the truss is 8 feet. And we've got our pinned supported A, so that's going to contribute 2 reactions, RAY and RAX. And then we've got a roller support at B, that'd be RBY. And then we have some geometry. We've got 4 feet from A to the line of action of that 10-kip force. And then we've got 8 feet from that line of action to B. So our free body diagram looks something like that. Get a little closer on that. There we go. So there's our free body diagram. And I'm going to define my coordinate system, standard coordinate system, X and Y, and positive moments. So just like the beam on supports problem, to solve the external problem, we find our sum of forces in the X and Y direction, and we find our sum of moments about a point. We should end up with at least one of those equations that we can solve directly, and then we can go back solve to find the others. So let's set up our equations. Sum of forces in the X direction, we've got a positive RAX. We have a positive 5 kips and nothing else. So not a whole lot in the horizontal direction on this one. Vertical, we have our sum of forces in the Y direction. We've got a positive RAY. We've got a positive RBY. And then we've got a negative 10 kips. Usually those 2 equations, the X and Y equations, are not ones that trip people up. There are 2 major issues with the moment equation, and I saw both of these come up on the exam as errors. 1, missing moments, forgetting the moment due to one of the forces, one or more of the forces. Second, forgetting the arm for the unknown force. If you get unreasonably high numbers, way higher than the applied forces, generally that's your error. You've forgotten the arm for the unknown force and just threw RBY in there instead of 8 RBY or 10 RBY or 12 RBY. So be careful about that. Every term in the moment equation has to have an arm and a force. So we'll take our pivot point at A here. That'll knock out RAY and RAX since they both push on the pivot point. But RBY will have a moment, since it's got an arm parallel, or it's an arm measured from A, the 10 kip force will have a moment, and so will the 5 kip force. That 5 kip force has a pretty substantial arm compared to the pivot point A. So we've got to take those all into account. So we're going to have 1, 2, 3 terms in our moment equation. So let's start with the 10 kip force. That 10 kip force, if I look at my line of action, that 10 kip force has a line of action that is 4 feet away from our pivot point. So that's the arm. 4 feet is the arm for that 10 kip force. So we've got 4 feet times 10 kips, that's 40 kip feet. And if we pin at A and pull down at C, we get a clockwise rotation, so that is negative. So we get negative 40 kips there, kip feet there. We've got this 5 kip force, and if we draw out the line of action for that 5 kip force, we're looking at this distance right here. That's the arm for the 5 kip force, the distance of closest approach. If you move this arrow around, the closest it gets to A will be 8 feet. That's the height of our truss. So the arm here is 8 feet, and 8 times 5 is 40. If we pin at A and push to the right at C, that'll give us a clockwise moment. Clockwise moments are negative. And then we have RBY. Don't just write down RBY. If you do, you'll end up with a huge answer for RBY. The moment caused by RBY, if we're pinning at A, the distance between the line of action of RBY and A is 12 feet. So we have 12 RBY. And if we're pinned at A and we push up at B, we get a counterclockwise moment. And counterclockwise moments are positive. So there we've got our equations of equilibrium. Since if we're in equilibrium, all of these must equal 0. Well, the x direction equation we can solve pretty easily. That's just going to give us RAX equals minus 5 kips. And that just tells us our assumed direction was incorrect, that RAX should have really pulled to the left instead of pushed to the right, which makes sense if you look at the loading. We've got something pushing to the right at C, so we've got to have something pulling to the left at A to oppose it. So we're going to hang on to that for a second. We'll see how we can deal with that negative in a moment. We can't deal with the y direction equation just yet, so we'll go to the moment equation. If we simplify that out a little bit, we've got negative 80 plus 12 RBY equals 0. Add 80 to both sides, we've got 12 RBY is a positive 80. Divide both sides by 12, and we have RBY is 6.6667 kips. And here I'm keeping 5 sig figs. And in this problem, I'm going to want to have 3 sig figs for my final answer. That's just arbitrarily selected. 6.6667 kips. That was another error that kind of crept up on the exam. People rounding off way too early. Don't round off to your final number of sig figs until you get to the end of the problem. Everywhere else you round to 2 sig figs more. So RBY 6.6667 kips came out positive, so we have verified our direction. And now that we know RBY, we can go back and figure out RAY, and RAY is pretty simple to solve, so I'll just draw it out. You can work through the math yourself on that, or see lecture 12. So RAY is 3.3333 kips. So that's our solution to our external problem. We have RAX, 5 kips to the left, RAY was 3.3333 kips up, and RBY was 6.6667 kips up. Now that's where we would stop in a typical non-concurrent force problem. But now we're into the second third of the class. So that means we have to go further with it. So I'm not going to round these down to 3 sig figs because they're not my final answer. They're a tool I need to get my final answer. So that is that's the external problem. And again, see lecture 12 for a discussion of why these forces are reasonable and how to look at this drawing and make sure that what you have as an answer is reasonable. Because if these are wrong, everything else downstream is going to be wrong too. So let's take a look at the method of joints. Let's dive into the internal problem. So in a truss problem, we're finding the internal reactions to these externally applied forces. In our problem, we have 5 and 10 kips externally applied, and we have the reactions externally applied. To be in equilibrium, the structure has to react to that as well. The structural members have to have loads that keep the structure from moving, that keep the whole structure in equilibrium. So we have to find the load and the state of each member. So each member carries a load, and it's either going to be in tension or compression, or it's unloaded. And we'll find in some problems, there are certain members that don't need to carry a load. Now that could be a way to tell us that that member doesn't really do anything and we can get rid of it, or it at least doesn't do anything for the loading that we've got. And it may serve a purpose in other loads. We finish up the problem by drawing either a table or a force summary diagram to communicate the state of each member to the reader. And I'll show you both of those here in our example problem. So the internal problem requires that we look at different free body diagrams. We can't figure out what's going on inside the truss by drawing the free body diagram of the whole truss. Remember that forces are only exposed in a free body diagram if something crosses a boundary or cuts through our system boundary. We need to look inside the structure. And the way we do that here is first with the method of joints, what's abbreviated as MOJ for method of joints, and MOS, the method of sections. Both of those are different techniques that are used to cut the truss up into different pieces and create new equilibrium problems with new unknowns, things we can solve for that we don't already know. We're going to focus on the method of joints. And the first step in the method of joints, as is the first step in the method of sections, is to find the reactions at the support, solve the external problem. We need that information going forward in almost every truss we solve. In the method of joints, you might guess from the name, it's going to have to do with the joints that connect the members together. The fundamental idea is that if the structure is in equilibrium, then every piece that makes up that structure must also be in equilibrium. So if we can draw the free body diagram of each joint, we can expose the forces that are on that joint. So we draw the free body diagram of each joint in sequence. We don't have to draw them all at once. We'll pick a joint, we'll draw the free body diagram of that joint, and then we'll solve the resulting equations. That'll give us some information that we didn't have before. Now, unfortunately, it doesn't give us everything. Remember that we can only get 2 or 3 unknowns in a problem and still be able to solve it. We have many more unknowns than that. In a typical truss member, or truss, we have 2 unknowns for each member. So in our 3-member truss that we're working on here, we've actually got 6 unknowns that we have to deal with. And we can't get that all in one set of equations. So we're going to get some part of that. And then we have to go do another free body diagram of another joint and use some of the information we learned from the previous step to solve the next one. So the fundamental component of method of joints is solving equilibrium problems, but we have to solve them iteratively. We have to repeat. So there's a repeat step here. Step 4 is to repeat steps 2 and 3 until we know everything there is to know about the truss. Basic rule of thumb in method of joints is if you have n joints in the problem, so if you have 5 joints, 10 joints, 12 joints, how many ever joints you've got, you're going to need to do n minus 1 free body diagrams of joints in order to solve the truss. So in the problem we're working on right now, we've got 3 joints. We're going to need 2 free body diagrams. We're going to do the analysis at 2 joints in order to get everything we need to know. So this can get complex pretty quickly because we can draw trusses that have 10 or 12 or 20 joints in them, and to solve those trusses by method of joints is going to require solving a lot of equilibrium problems, to the point where we usually just write a computer program to do it. So we're not going to have to do too many of them. We won't have to do more than 4 or 5 at most, and usually some of those are pretty simple. But the other method we'll look at, method of sections, does a little bit better job on those larger trusses. In the end, once we've got everything we need to know, we draw a force summary diagram, use a table to illustrate the loading on each member, and communicate our final answers. So let's see how it works. So we'll go back to our typical truss problem here. And first thing I'm going to do is carry our information forward into a new drawing. Good idea generally, once you've solved the external problem, to resketch the problem with the right forces drawn in. So if you found places where your assumptions were wrong, that's the point to correct them. So over here, I'm going to redraw my truss with members, with 3 members here. And I mentioned last week that we name the members based on the joints. So this horizontal member is member AB. This member off to the left is member AC. This member on the right side is member BC, and we always name them in alphabetical order just for consistency and ease of communication. So we're not saying member BC and member CB and thinking they're 2 different members. We had 5 kips pulling to the left there, and we had 3.3333 kips here. We had 6.6667 kips there, and we had our 5 kips there. Our 10 kips down. We had our geometry of 8 feet. And just quickly sketched in here 4 feet and 8 feet. So there is what we've got after we've done the external problem. We've got our reactions. Our next step is to isolate one of the joints. So we have to pick one of the joints to work with. And piece of advice in solving truss problems is, if you want to start with a joint that's going to be simple to work with, and usually the simplest ones to work with are the ones that interact with horizontal members. If a member is horizontal, then it's only got force in one direction. And that means something we don't have to take a sine or a cosine of, so it's a little bit easier to deal with. So joint C here would not be a great candidate to be working with because it's got a couple different angles and there's going to be different sines and cosines, and it's going to be a mess. So A or B would be a good place to start. And just out of habit, I'm going to start at A. And so the principal method of joints tells us to isolate joint A. So here I'm drawing my system boundary around joint A. Anything that touches or crosses that system boundary needs to be represented by a force. So down here, I'm going to draw my free body diagram for joint A. So there's joint A. It's got a 5 kip force pulling to the left. It's got 3.3333 kips pulling up or pushing up. And we've done these kinds of problems before where we're drawing all our forces at one point, and it's always going to be easiest to move that force so that the tail is at the joint. It gets a little confusing when the head is at the joint. So nothing will change if you move that 3.3333 kip force up like that. And then we've got these other two members that we're cutting through. Those members have to exert a force on joint A. And it's not always going to be clear what direction that force is in. Sometimes you just pick which direction based on what's going to be easiest to draw in the free body diagram. So you're going to make guesses here, and hopefully they'll be intelligent guesses and educated guesses, and a lot of times they will be, but sometimes it's complex enough that you really can't make a good guess. So be assured, though, that any guesses you make will be sorted out by your math. Same method that we saw before. If the answer came out negative, then we've got our assumption wrong. So we've got member AB here, and the simplest assumption for me to make here is that member AB pulls on joint A. So it exerts a force like that. And that's just easiest to draw, because drawing it on top of the 5 kip force, as if it was a push, that'd be a lot harder. Now we've got to label that force something, and I'm going to label it F for force, but then with a little subscript, AB. That subscript tells us that member AB is responsible for that force. Then we've got this other member up here. We've got member AC. And I've got two choices. Either member AC pulls on joint A or it pushes on joint A. Those are the only two options. A member can either push or pull. Well, if I drew it as a pull, I'd have a problem here. Remember that we're looking for equilibrium. And an equilibrium is a tie that no one's winning. It's a tug of war that no one's winning. If I pull up and to the right with this, there's nothing pulling down. So sometimes you can make a pretty good guess based on what your free body diagram looks like and what it has to be in order to be in equilibrium. So the only thing that would make sense here is that if member AC is pushing on joint A, so it's going to have a force that looks something like that, and that's going to be FAC, force due to member AC. Now, hopefully that free body diagram looks pretty familiar. It's a concurrent force problem. It's the same kind of problems we worked with in beginning equilibrium, looking at these at the box on a wire problem and things like that. This is essentially a non-concurrent force problem. All the forces intersect at, a concurrent force problem. All the forces intersect at one point. So we don't have any moments here. We're just going to have forces in the X and the Y direction. Now, if you remember solving concurrent force problems, that brought us two unknowns. And we have exactly two unknowns here, FAB and FAC. We don't know what either of those are. We do need one more piece of information, though. We need an angle. We need to know something about what this angle is right here, or what the angle is down here. We need something, because we're going to need to take sines and cosines to figure out our X and Y components. Fortunately, that can come from the drawing pretty easily. So if we look at the drawing here, we've got a triangle, a right triangle right here, that has an 8-foot height and a 4-foot base. We can figure out this angle right down here in the corner by using the inverse tangent. Inverse tangent of opposite over adjacent. So if we take the inverse tangent of 8 over 4, we get 63.435 degrees. So this is 63.435 degrees. Now, be careful translating that down here into the free body diagram. Very common error, somebody puts it in the wrong place. Be sure about it. Draw what you've got down here for your force and your arrow up here. And if you look at if you draw kind of a cross here, or an X, angles that are opposite each other are the same. So the angle I've got here is the same as this angle down here. So it's this one that's 63.435 degrees. So be careful with that. It can get problematic if you put the angle in the wrong place. Your sines are going to be cosines and vice versa, and you won't get anything right. So there we've got our free body diagram for joint A. And we can use our sum of forces in the x direction equal to 0 and sum of forces in the y direction equal to 0 to figure out FAB and FAC. So let's set up our equations of equilibrium. Sum of forces in the x direction. Well, we've got FAB positive. We've got 5 kips negative. We get nothing from the 3.333 kips because that's just straight up. But then we're going to pick up a piece of FAC. Which piece? Well, the horizontal piece. And if we're using this angle 63.435, that's going to be the adjacent piece. And adjacent goes with cosine. So we have FAC, whatever that is, times the cosine of 63.435 degrees. And that, by assumption, is to the left. So negative. So that's our x direction equation. We have all of FAB. We have all of this 5 kips to the left. And then we have the horizontal piece or the adjacent piece of FAC. So FAC cosine 63.435. In the y direction, we have all of this 3.333, 3 kips force up, so that's positive. We get nothing from FAB or the 5 kips because those are both horizontal, all x, no y. And we're going to catch a piece of FAC. Which piece? Well, it's going to be the opposite side. It's going to be the vertical piece. It's the other part that we didn't see up here. So if you're pretty confident that this is cosine, you can be equally confident the other one's going to be sine. And that's down, so it's going to be minus FAC sine of 63.435 degrees. So those were our equations of equilibrium. Because this joint is in equilibrium, sums must be equal to 0. Now, unfortunately, we can't solve the x direction equation right away. We're missing too many pieces. We don't know FAB and we don't know FAC. So we go to the y equation. Well, the y equation just has one unknown, FAC. And this is the kind of equation we've solved before, and we can solve this by adding FAC sine of 63.435 to both sides. We'll get 3.3333 equals FAC sine 63.435 degrees. We can divide both sides by the sine. That'll cancel out the sine on the right. And if we go to our calculator, 3.3333 divided by the sine of 63.435, that gives me that FAC equals 3.7267. And this is force. Our units are in kips, so kips. So that's member AC's load. Member AC carries a load of 3.7267 kips. It came out positive, so it means our assumed direction over here is correct. I'll come back to that in a moment because we're going to need to use that to interpret whether our member is in, whether this member is in tension or compression. But FAC 3.7267 kips. Now that we know that, we can go back up to the X direction equation and plug that in. We've got FAB minus 5 minus 3.7267 cosine 63.435. And if we go to the calculator, 3.7267 times the cosine 3 of 63.435. We get, so FAB minus 5 minus 1.6666 equals 0. And then solving that one's relatively straightforward. It'll give us FAB is a positive 6.6666 kips. So that came out positive too, which means our assumed direction for FAB is correct. So that is the beginning of the method of joints. That's one joint solved. And in one joint, we have figured out two of our truss members. We figured out the load that member AB carries. Member AB is carrying 6.6666 kips of load. Member AC is carrying 3.7267 kips. But just finding the loads, only half the story. We need to know whether those members are in tension or in compression. And this is a big point. This is something to be really, really careful of, because it's another place where many people make errors, because it is and seems counterintuitive at first, but if we're really careful with it, it'll make sense eventually. You just have to work with it a little bit. So let me jump back into the notes for a second. We'll come back to this and finish up the problem. But if we go back to the notes, we can take a look at tension versus compression. There's a little bit of confusion here with tension versus compression because of what we're looking at. We are looking at the joints, not the members. Pretty clearly, I think it makes sense to everyone. If you grab hold of a piece of metal and you pull on it to stretch it out, you're putting that piece of metal into tension. You are trying to stretch it out. Think of a slinky, for example. You grab hold of the ends of a slinky and pull your hands apart. You're putting that slinky into tension, and the tension causes the slinky to stretch out. On the other hand, if you squeeze the ends together, that's compression. The member experiences a compressive force. But what we're looking at when we do method of joints is not directly the force on the member. We're looking at the force on the joint due to the member, and that causes some confusion. So essentially, we're looking at the loads in a mirror. We have this little thing called Newton's third law that says that when you exert a force on something, you get an equal but opposite force back. And I think the simplest way for me to explain that and help you to see where that confusion is to imagine, put yourself in a little bit of a thought experiment. Imagine a big rubber band. Something that's maybe a big O-ring or something like that I'm gonna have you hold on to, and I ask you to close your eyes and put your hands out. If I stretch out that rubber band and then put it on your hands, even though that rubber band is in tension, your hands are going to feel pushed toward each other, because a member that's in tension is trying to shrink back down to its original size. A member in tension tends to pull its supports inward. Flip that around and think about a spring. If I take a spring and compress it and hand it to you, the first thing you're going to feel when you hold on to that spring is that it's pushing your hands out, and you're going to have to push harder in to hold on to it. A member in compression tries to expand back out, so it tends to push its supports in the opposite direction. It tends to push its supports out. So even though to squeeze something down, to squeeze a spring down, you'd have to push in. You're pushing in because your hands are being pushed apart by the spring. So we have to be very clear about what we're looking at. And when we're looking at the supports, the forces are exactly opposite what you'd expect them to be, because we're looking at it through the mirror of Newton's third law. So the force directions are counterintuitive. It's easy to make an error. And at first, one of the things you can use to help you get the right answers here is at first, of course, the first pass at this is get the right answers. Figure out how to get the right answers. Understanding will come in time. Look at what you think the answer should be and then answer opposite. I can tell you that'll work with most people. That if you think just by looking at it, well, obviously this member's in tension, it's in compression, and vice versa. It'll take a little bit of time, and I'll draw some pictures to help you decode it at first until it makes sense to you. But it's a problematic area, so you got to be very careful. The issue here is about point of view. It's about what body are we drawing the free body diagram of. And it comes down to Newton's third law. In a truss, the structural members interact at the joints. They push and pull on each other at the joints. When we isolate a joint, we're looking at the forces on the joints because of the members. We're looking at the reaction forces. Think about a simpler example is just think about standing on a floor. When you stand on a floor, the force that you're applying to the floor is down, gravity. But the force the floor is applying to you is up, equal and opposite. It's exactly the same situation in dealing with a joint and a member. When that member is exerting a force on the joint exerts an equal but opposite force on the member. And what we find are the forces on the joints due to the members, not the forces the members themselves directly experience. Interpreting tension and compression is easiest from the member's point of view, not from the joint's point of view. From the joint's point of view, everything's flipped around 180 degrees. So it's always easier to see tension and compression based on looking at the forces on the members due to the joints. But we solve in our equilibrium problems the force on the joints due to the members. Those are reactions to each other. They're equal and opposite forces. So take, for example, a picture like this. Here is a member that is experiencing a force. This would be considered, for example, the free body diagram of the member. So it's everything from the member's point of view, and the member feels squeezed in. That's compression. But from the point of view of the things doing the squeezing, the free body diagram of the joints are going to show an equal and opposite force. So the force on the member due to the joints will show up in a free body diagram of the member. The free body diagram of the joint will be in the opposite direction. So if you draw the free body diagram at the joint, you use the force on the joint due to the member, and that's in the opposite direction. So for example here, in these two pictures, and this picture here, this slide is probably a good one to stare at for a while to make sure that things make sense. What is being shown here is a faint outline of the member. The member's not really there. It's just drawn for reference. What we're really seeing here are parts of the free body diagram of the joints at each end of the member. The top member is in tension. When a member is in tension, that's that stretched out rubber band. If I grab onto a stretched out rubber band that's already been stretched out, my hands are going to feel pulled in. And that's the hallmark of a member in tension. If the force on the joint is inward toward the member, that member is in tension. So that's what tension would look like at the left or the right end of the beam. Now, of course, if it's inclined or anything like that, it's the same idea. If the force that you find in your free body diagram of the joint points inward toward the middle of the member, that member is in tension. Down here, we've got a member in compression. I've squeezed a spring together and handed it to you. If you're not ready for it, your hands are going to fly apart. That's exactly what's happening to the joints here. The joints are being pushed apart by a member in compression. So this is the hallmark of a member in compression. The joints are pushed apart, away from each other. So the members in compression push the joints away. Members in tension pull the joints together. So I would print out that slide, circle around it, take a screenshot, whatever you need to do. Use this at first to figure out whether the members you're working with are in tension or compression based on the free body diagram. So let's jump back to our drawing here and see if we can figure out tension or compression based on what we've got. So the thing that I like to do at first here to look at tension or compression is to sketch the members in, maybe even in a different color. But this is joint A. Joint A is right up here. Member AB is to the right. So member AB looks something like that. Broken line. That's part of member AB right there. So member AB is exerting a force on joint A that pulls that joint in toward the middle of the beam. That's tension. I know it looks like, because you want to say, I know you do, you want to say that this joint, it looks like it's pushing the member together, so the member should be in compression, but that's not what we're looking at. This force is not the force the member feels. This is the force the joint feels because of the member. So the member is pulling the joint in toward the middle of the beam. Only things that are stretched out could do that. This is tension. So member AB is in tension. And so I'm going to put a little parentheses right next to that that says T. And usually the way we do this is we'll draw a table. And this is what I'd encourage you to do on your homework assignments, things like that. We're going to have 3 rows in the table. We've got member AB, member BC, and member AC. And usually we try to do it in alphabetical order. So A, B, A, C, B, C. It's probably a better way to go. This would be the member. There's going to be a load on that member, and it's a good idea to put your units in there. That way you don't have to rewrite the units in the table. And then I usually like to write just T or C, tension or compression. So we've figured out here that member AB carries a load of 6.6667 kips, and it's in tension. So I'm going to X the box that says tension. So member AB is in tension. Member AB pulls joint A in toward the middle. Let's look at member AC. Well, where is member AC compared to joint A? Well, it's up and to the right. So member AC is over here, like that. So member AC appears to be pushing joint A away. Because both our answers came out positive, so our directions are right here. So member AC is pushing joint A away. Only things that are compressed can push things away. So member AC is in compression. So we figured out that member AC carried a load of 3.7267 kips, but member AC is in compression. So if you're feeling a little confused right now, especially with respect to tension and compression, go back and review the video, watch this section again and again and again until it makes sense, or until you're at least willing to accept that when the joint shows an arrow toward the middle of the member, it's tension, and when the joint feels a force away from the member, it's compression. You can take that for fact right now and just use it as a tool and understand it later, or spend the time up front here now thinking about it and trying to figure out a way for it to make sense, because it is right. So I'm not going to belabor that anymore. You can go back and look at the video on it for that. So let's see how we can proceed and finish up the problem. You'll notice our table is still partially empty. We didn't learn anything about member BC. Joint A doesn't touch member BC, so there's no way to get information about member BC from joint A. We need another joint. So we're going to use joint B. We can draw a second free body diagram of joint B. So if we go down here, we'll draw a second free body diagram. There's joint B. And if we look at joint B, there are three forces interacting at joint B. We've got our reaction force at 6.6667 kips, and that's up. And I'm going to draw that as a pull upward, 6.6667 kips. Then we've got one member we already know. We know what's going on with member AB. Member AB is in tension, and members that are in tension pull the joints inward. So we know everything about what's going on with member AB at joint B. This is not a guess. We know that joint B is going to be pulled to the left. Since joint A is pulled to the right, the joints are pulled together when a member is in tension. When something's stretched out, it tries to shrink back to its original size. So it's pulling those support points inward. So down here in our free body diagram, we don't have to label it as FAB. We can put a number on it. We know what it is already. Member AB is 6.6666 kips. A little bit of round off error there. And then we've got member BC. Now, member BC, we don't know anything about. So we're going to have to take a guess. And if you look at your free body diagram, there's really only one reasonable guess. Member BC has got to push joint B down and to the right. It's the only way it can go. If it pulled up and to the left, we wouldn't have equilibrium. So this is member BC's force. Now we're going to need an angle, and we can go up to our drawing for that. We'll need this angle here, but again, we've got a triangle, got a right triangle, 8 feet high and 8 feet on the base. So hopefully we don't need too much of our calculator's help for this one, but no shame in going to your calculator and figuring that out. But it's the inverse tangent of 1. That's 45 degrees. So this has got to be 45 degrees here. And again, try that X trick here. If you draw these out, you'll figure out which angle it's got to be. Now, of course, at 45 degrees, it doesn't make any difference, but we're dealing with our angle to horizontal here. So we've got 45 degrees there in our free body diagram. So there's our free body diagram. Now notice there's only one unknown. This happens at the last joint that you need to do for the problem. At the last joint, you'll only ever need to set up one equation. So it's up to you whether to use the X or the Y direction equation. I'm going to use the Y direction equation here. The reason is this number is a little bit nicer than this number. To get this number, I had to do a bunch more calculations. I had to do everything up here. That means there's probably more round off error built into this number. This is not as much round off error. This just came from my external problem. So I'm going to get a better solution using the y direction equation. The x direction will work, and when we round this off to 3 sig figs, it's not going to be a problem. But and you could use the x direction equation, but only one equation is going to be needed because we only have one unknown. So let's do our sum of forces in the y direction. So we've got a positive 6.6667 kips up, and we've got a piece, the vertical piece, opposite side, so that's sine FBC sine of 45 degrees. And that equals 0. So if we set up the solution here, we'll have FBC sine of 45 is 6.6667. Divide both sides by the sine of 45. And we'll get that member BC carries a load of 9.4281 kips. 9.4281 kips. And that came out positive, which means our assumed direction is correct. It had to have been. There was no other way it could be in equilibrium, and we knew exactly these two. There's no error there in the directions. So member BC, we can go up to our table now and fill that in, 9.4281 kips. But we still have to figure out if it's in tension or compression. So take a second and think about that. If you're watching this on the video, pause it and try to think of whether we're in tension or compression. Now, if we follow the same principle we did up here, we can sketch the members in. Here's member AB. It's the right-hand side of member AB, but we don't need to worry about that one. We need member BC. Member BC is up here. So member BC is pushing joint B away. Members that push away, they're in compression. So member BC is in compression. Now with simple trusses, you can kind of see that from the loading. Here we're pulling down. If you imagine, use your imagination a little bit and try to think about how this would look if it starts to fail. You know, kind of play that video. A lot of people in this field have a pretty good intuition about these things. Imagine what would happen if that, instead of 10 kips, that was 100 kips or 1,000 kips, and the structure starts to fail. How is it going to fail? Well, if you pull down really, really hard on that, these two members are going to want to buckle. They're going to want to kick off to the sides. This member down here is going to try to stretch out. You can visualize tension or compression. Member AC and member BC are in compression. Member AB is in tension. And that's generally how it works out in these kinds of trusses. The horizontal parts tend to be in tension, while the vertical parts tend to be in compression. Now, if this 5 kip force over here was a little bit more, or a lot more, it might push hard enough to put AC into tension. It's why member BC is carrying way more load than member AC is, because member BC is getting pushed on even more from that 5 kip force, and that's kind of pulling a little bit on AC, canceling out a little bit of that 10 kips pulling down. So if you go back and look at the truss, a lot of times you can reason things out and validate your answers, or at least have some idea that your answers have a chance of being correct. So that's the solution to the truss problem. The only thing that remains is to draw our force summary diagram. And this is a good way to go to finish up the problem. And the way we finish up the problem, we go back to our original truss, essentially our original drawing. We draw in everything we've learned. So we've got our 5 kips here. We had our 3.333 kips there. We had our 6, and we can round at this point to our 3 sig figs. So this would be 3.333 kips, 6.66 or 6.67 kips. We've got our applied load, 10 kips and 5 kips. About the only thing I'd leave out is the geometry. Don't put in angles, don't put in lengths or anything like that. You can label A, B, and C, but right along each member what the load is and whether it's in tension or compression. So AB was 6.67 kips in tension. Member AC was 3.73 kips in compression. So parentheses with a C, and then 9.43 kips in compression. So that's our force summary diagram. So that communicates everything we've learned. And it's rounded off to our final number of sig figs. So that would be our force summary diagram. Now we're going to do lots of examples. We're going to do lots of practice on these because although the individual steps are not necessarily hard on their own, there are a lot of them. And the tedium of working through one of these can become problematic after a while. So we will be practicing a little bit more with them both tonight and on Wednesday. Wednesday we'll just be doing some example and practice problems in method of joints. So that brings us to just about the end of our lecture time. Are there any questions out there?
Nope.
All right. Well, we'll pause for a few minutes here for a little bit of a break, and then I'll put another problem up. We'll have you work out on your own, at the very least, the external problem, and then we'll kind of walk through the internal problem as another method of joints example. So let's take a break. Back in a few minutes. All right. So here's our practicum problem for the evening. We've got a 5-member truss, so a little bit more than the 3-member truss we worked on a little bit earlier, but there are lots of right angles, so that's not too bad. We have 5 members to figure out, and we've got to find load, tension, and compression for those, and we'll do this to 3 sig figs. So 3 sig figs for our final answers. So take a few minutes and work out the external problem, and we'll do a check on that, and then we'll step through as another example how to do the method of joints on this problem. All right, so first step in solving the truss using the method of joints is to solve the external problem. So we need a free body diagram for the truss as a whole. So I'm going to try to keep the main sheet here clutter free, so I'll do that on a separate page. So we've got our truss itself, and we don't really care much about the internal structure for solving the external problem. So whether you draw the cross member there or not doesn't really make any difference. So we're not going to use it. We've got 3 kips there at A, or it's at D. We've got 5 kips here. We've got 10 kips there. Then we've got our reactions at our supports. So we've got a pin support at A, so that's going to generate an RAY and then RAX. And then we've got a roller at B, so that'll be RBY. So there's our free body diagram of our external problem, coordinate system, X, Y, and moments. So let's build up our equation. Sum of forces in the X direction We've got RAX positive, and we've got 10 kips positive. In the Y direction, we've got RAY and RBY both up. We've got 3 kips down, and we've got 5 kips down. So we've got a total there of minus 8 kips down. So just to jump ahead a little bit in the math, 3 plus 5, 8, both pushing down. So minus 8. Then we've got our moment equation. And I'll pick point A. So first, let's go through and see which forces will have moments. Definitely RAY and RAX will not have moments because their lines of action go through the pivot point. This 3 kip force will also not have a moment since its line of action runs right through the pivot point. Essentially, its arm is 0. But the 5 kip force will definitely have a moment. The 10 kip force will have a moment. Its line of action does not go through the pivot point. And RBY will have a moment. So we're going to have 3 terms. Got to sort out the arms. The arm for the 5 kip force is the distance between RAY and RBY. And that, according to our drawing here, is 10 feet. So the arm for the 5 kip force is 10 feet. So that'll be 50 kip feet clockwise. So clockwise is negative. So we have negative 50 kip feet there. The 10 kips force, if we trace out its line of action, that 10 kips force is 4 feet away from A. So we've got 40 kip feet. If we're pinned at A and we're pulling to the right at C, that would be a clockwise moment, and clockwise moments are negative. So we have minus 50, minus 40. Minus 50 from the 5 kips at 10 feet, minus 40 from the 10 kips at 4 feet. And then we've got RBY. RBY has an arm of 10 feet. So 10 RBY positive. Since if we're pinned at A and we're pushing up at B, that would be a counterclockwise moment. So there we are. This is equilibrium, so all the sums have to equal 0. Solving the x direction equation, RAX is a negative 10. That means our assumed direction was incorrect. I assumed here in my free body diagram that RAX was to the right. It's really got to be to the left. So RAX is negative 10 kips. Jump to the moment equation because we don't have enough to solve for the y direction equation. Negative 40 minus 50, that's negative 90. So we have negative 90 plus 10 RBY equals 0. And solving that's relatively easy. 10 RBY equals 90. So RBY equals 9 kips. Now that came out positive, so we can be relatively confident in our assumed direction for RBY. Let's go up to the y direction equation now and figure out RAY. Well, if we are careful here, RAY plus 9 minus 8 equals 0. 9 minus 8 is 1. So I have RA1 plus 1 equals 0. And when I subtract 1 from both sides, that gives me that RAY is negative 1. So RAY came out negative. That means our assumed direction is incorrect. And that might have been hard to spot. You might have seen from the beginning, well, yeah, that RAX is in the wrong direction because I've already got something pulling to the right. I need something pulling to the left. But that RAY came out negative, that might have surprised you. And the issue here is that 10 kips pulling here, that 10 kips is trying to rotate everything around B. So it's picking up at A. This 3 kips down here is not enough to counteract that. It's helping. Without that, we'd have a much bigger force that we'd have to pull against. That 3 kips is definitely helping, but RAY is negative. So RAY comes out negative. That means our assumed direction was incorrect. So that's our external problem. So to proceed, I'd go back to the original sheet and resketch my drawing with the correct directions on the arrows. So I have 10 kips there and 1 kip down. And I had 9 kips up. Made 10 kips there, 5 kips, and 3 kips. And then we'll just read the geometry off of the original problem. So that's how the forces lay out. So that's our external problem. Step 1 in solving the truss. So we don't have our table filled out yet, but we do have our reaction forces nailed down. And that's a pretty good start on the problem. If this was a problem being evaluated out of 100 points, this would probably be a good 20% of it. It's just getting that external problem solved. Any questions there?
Nope.
All right. So now let's go into method of joints. So I will copy over my labels here, A, B, C, and D. So to do method of joints, we need to pick a joint, draw that joint's free body diagram, and from that, we'll figure out what 2 of the unknown forces are that interact at that joint. We have to be careful though, we can't just pick any joint to start at. There are a couple joints in this problem that we can't use yet. We can't, for example, use joint B. And the reason we can't use joint B is because there are 3 unknowns there. We don't know what's going on in member BC, we don't know what's going on in member BD, and we don't know what's going on with AB. We have to be careful about what joints we pick. We can't just go in and pick any joint to start with. If a joint has more than 2 unknowns, it's not going to be a reasonable place to start. You can write the equations down, but you're not going to be able to solve them. There are too many unknowns. So joints B and D are out to start with. We don't have enough information on those. Joints A and C, however, we could work with. Joints A and C, we have 2 unknown members. And then we have our externally applied loads or our reaction forces. So I'm going to start at A because it doesn't look like it's going to be any easier than C. And it's comes alphabetically first. So I'll go with A first. So let's draw the free body diagram for joint A. So I'll draw that down here. There's joint A. I've got 1 kip of force pulling down. I've got 10 kips of force to the left. Then I've got member AD, which is either going to be pulling up or pushing down, since the forces due to members can only be along the length of that member. And member AB, which is either pulling to the right or pushing to the left. Well, just based on my free body diagram, the easiest way to draw both of those is as pulling. So member AD, I'm going to draw that it pulls on joint A, and that'll be FAD. And then member AB, I'm also going to draw that it pulls on joint A. So there's FAB. So that's the free body diagram of joint A. And if you're ever in doubt about whether you've gotten all the forces, draw a little circle around that joint and make sure that the count of what crosses that circle matches what you've got in your free body diagram. Here I cut through 2 members, member AB and member AD. I've got those, and I cut through the reaction forces, 10 kips and 1 kip. So those are there. So always worth the time just to take a few seconds and look at your free body diagram and make sure that it's a reasonable representation of the joint that you're drawing. And we've got our coordinate system there. No need for moment since this is a concurrent force system. So let's build up our equations of equilibrium. Sum of forces in the x direction. Well, I've got all of FAB to the right, so that's positive. And I've got a whole bunch of 10 kips to the left. So I've got all of 10 kips to the left, negative. Nothing else there in the x direction. So we go on to the y direction. Sum of forces in the y direction, I've got a positive FAB and a negative 1. Well, since the whole truss is in equilibrium, every little piece of that truss needs to be in equilibrium too. That means joint A is in equilibrium, so the sums must equal 0. And so we get two equations that hopefully pose no problem for anyone to solve. You can hopefully solve those by inspection and say, well, obviously FAB has to equal 10 kips, and FAD has to equal 1 kip. If you look at your free body diagram, it's the only thing that makes sense to set up a tug of war that no one wins. If we've got 10 kips to the left, we better have 10 kips to the right. If we've got 1 kip down, we better have 1 kip up. So both of our answers came out positive because our assumed directions were correct. So we can go to our table and fill in FAB is 10 kips and FAD is 1 kip. But we have that unfortunate task of figuring out if these members are in tension or compression. So what I would do in your first several problems that you're working with this is draw this somewhere on your page. There is a some prototypical member. If the forces are inward, that's tension. If the forces are outward on the joint, so I'm drawing these dots in here really prominently to show that those are the joints. So that's tension and compression. Now, if you just looked at that without having the context of going through the discussion, you might think that looks totally and completely backward. But remember, what we're looking at here is kind of a shaded out ghost image of the member. We're really looking at the joints. And a member in compression has been squeezed. It's trying to expand back out to its original size. And so it's going to push against its supports. And it's going to push them outward. A member in tension, think about these as pegs in the wall. If you take 2 pegs and drive them into a wall, take a big rubber band and stretch it out and hang that on those pegs. If those pegs aren't strong enough, they're going to fly inward. That's what tension does to supports. Tension draws the supports inward while compression pushes the supports apart. So this will be your guide until it makes more intuitive sense to you of how to look at it, to how to check the boxes. Go back to your free body diagram and sketch in the members. Sketch in the ends of the members that deal with that joint. Well, member AD is above joint A, so right there is member AD. And member AB is to the right of joint A, so there's member AB. Well, both of these are pulling their forces, FAD and FAB, inward toward the middle of the beam, toward the middle of the member. It looks like this picture here. It looks like tension. And it is. So this end right here, that's what we're looking at right there. This end rotated 90 degrees, that's what we're looking at there. So both member AD and member AB are in tension. It's the only way they can be pulling on their supports. Only members in tension, things that are stretched out, have the ability to pull things inward. So that's joint A. So the math wasn't too hard on joint A. We got a nice simple free body diagram that tends to happen when only 90-degree angles are involved. And we had to interpret tension or compression. We'll go back to the physical discussion here once we're finished with the problem and take a look at why member AB and AD have to be in tension. Any questions at joint A? Anything not quite clear in the process for joint A?
No, we're good.
All right. So let's jump to joint C. Now, if you look at joint A and you look at joint C, they look pretty similar to each other. So you can expect a similar level of mathematics. Let's draw the free body diagram for joint C. For joint C, I've got a 5 kip force down. I've got a 10 kip force to the right. Always start with your known forces. It'll make drawing the unknown forces a lot easier. Then we've got member BC. Well, the simplest way to draw that in this free body diagram is to draw it as pulling up or pushing up. So this will be FBC. And for member CD, easiest way to draw that in is if it's pulling to the left. So we'll draw that over here as FCD. So there's our free body diagram. And hopefully I don't have to work through the math on that one. You can set up the equations exactly the same as you did at joint A. I'm just going to jump to the answer here, and hopefully that's pretty straightforward. Member CD has got to be 10 kips, and member BC has got to be 5 kips. You know, it's straight and level flight, right? Lift, drag, thrust, and weight. They're all equal and opposite. So FCD got to be 10 kips, FBC got to be 5 kips. Everything comes out positive. You can prove that with the equations if you need to, but that's how the answers come out. So we've got our answers for members CD and BC, so we can draw those in. Member BC carries a load of 5 kips, and member CD carries a load of 10 kips. But we still need tension or compression here, so let's sketch in the members. We're up here at joint C. At joint C, member CD is to the left and member BC is below. So let's bring that in here. Member CD is to the left, so it's going to look something like that. And member BC is below. So that's what that corner of the truss looks like. It's the upper right corner. So the members have to be down there. And then be careful to make sure you're looking at the right forces. You're always looking at your unknown forces to figure out tension or compression. Don't look at the 5 kips or the 10 kips. Just focus on the unknown forces that are associated with that member. Well, look at CD. Member CD is pulling joint C to the left. So you can go to your picture here and see which one does it look closer to. And hopefully you draw the conclusion, it's tension. So let's see if I can get those both on the screen at the same time here. There's my diagram for tension at the right end of a beam. There's the right end of member CD pulling its reaction force, its force inward. So member CD is in tension. So member CD, I can check the tension box on that one. Member BC, on the other hand, is down below here. It's pushing joint B away. Kind of looks like this end of the beam if I rotated everything 90 degrees. Compression. Member BC is in compression. So I'll check the compression box on that one. So take a look at the free body diagram, look at how the members lay out compared to the force associated with that member, not the applied forces, but the force associated with that member, which you solved for, FCD, FBC. What their directions are compared to the member will tell you whether it's in tension or compression. And until it makes more intuitive sense to you, use this guide. Use that to decode whether you've got tension or compression. Think of this as a tension compression decoder ring. So it tells you exactly whether you've got tension or compression based on comparing the picture. So that's joint C. Any questions there?
Nope.
All right. So we've got to do one of joint B or joint D. This is a four joint problem. We have to solve three of the joints. It's always one fewer joint than what you've got. So we can either do joint B or joint D. I don't think one or the other is any harder in particular than I suppose if I was really pressed to choose one as better than the other, I might say joint D is better because all that interacts with is information we've been given and just a couple things we've calculated. Down here at B, we calculated this 9 kips. So if we were wrong in that, that could throw things off. But if we're wrong in that, everything's going to be off anyway, so it doesn't make any difference. Because all this side would be off too, and A would have been wrong. The only thing that wouldn't depend on the external problem is what we did at joint C. Nothing there cares about what we did at the reactions. So it's a toss up whether you do B or D. I think I'll just do B since it's down here. So let's draw the free body diagram for joint B. And if we look carefully at joint B, if you draw your circle around joint B, you're going to see four forces that are interacting there. I've got that 9 kip force. I've got member BC, I've got member AB, and I've got member BD. But I know what's going on at member BC. I know what's going on with member AB. So I really only have one unknown here, which means I only need one equation. At the last joint, we only ever need one equation. So let's draw the free body diagram here for joint B. So at joint B, I've got 9 kips up. Let's deal with member AB first. Member AB, according to our table, member AB carries a load of 10 kips in tension. So here's what tension looks like. We're on the right side of the beam, so I should draw my 10 kips to the left. Member AB is in tension, so it's trying to make joints A and joint B closer to each other. It's trying to shrink back to its original size. So it's got to pull the joints close to each other. You got to nail not only the amount of force, but the direction in order for your free body diagrams and your solution to work out when you carry information from one joint to the next. So that 10 kips from member AB pulls to the left. Then we've got member BC. Well, member BC, according to my drawing here, is 5 kips compression. In compression, the joints are forced away from each other. Something that's been compressed is trying to expand back out. And when it expands back out, it makes its supports farther away from each other. So members or joints B and C are getting further away. So joint C is being pushed up, joint B is being pushed down. So that 5 kips from member BC has got to be down. I'll draw that on the other side here, 5 kips. And then we've got member BD. So member BD is off to the upper left. And we've only got two choices. Either it's going to pull joint B to the upper left, or it's going to push joint B to the lower right. And if we look at our free body diagram, only pushing to the lower right makes sense. If it pulled to the upper left, then there wouldn't be anything to the right. You can't have equilibrium that way. You can't have something to the left without having something to the right. So it makes the most sense to draw the force due to member BD down and to the left, down to the right, excuse me. We need an angle though. We need an angle because we're going to need sines and cosines in this one. So if we go back up to our free body diagram, or to our original free body diagram here, kind of draw those members out, this angle and this angle would be the same thing. Well, I can get this angle here by looking at this right triangle. That right triangle right there has a height of 4 feet and a base of 10 feet. So we can use the inverse tangent of 4 over 10 to get the angle, and that'd be 21.801 degrees. So 21.801 degrees. And that'll be the same angle here, 21.801 degrees. So there we've got our free body diagram for joint B. Coordinate system. And there we go. Now we only have to do one of the equations, either the sum in the x direction or sum in the y direction. I'm going to pick sum in the x direction because I'm lazy and I don't want to have to add an extra term in here. If I go the x direction, all I've got to do is deal with this 10 kips. If I do the y direction, I'm going to have to deal with the 9 and the 5. So that's extra work. So I'm going to go with the x direction equation. So we take our sum of forces in the x direction. We've got a negative 10 kips to the left. And then I'm going to catch a piece of FBD. It's going to be the adjacent piece, the horizontal piece. And adjacent goes with cosine. So I have FBD cosine of 21.801 degrees. That's to the right, so it's positive. So there's my x direction equation. I don't have to bother with the y direction equation. I'd get the same answer. So this is equilibrium, so that sum is equal to 0. And if we solve the equation, we've got FBD cosine of 21.801 degrees equals a positive 10. Divide both sides by the cosine of 21.801. And we'll get cosine divide 10.770 kips. So FBD is 10.770 kips. Now, if you use the y direction, you might have gotten 0.771 in many problems. We haven't rounded anything up to this point. So assuming our numbers are right, everything's exact until we round it here. So chances are, no matter which way you work this one, you'd get 10.770. Normally, there'd be more round off error built in, but I kind of picked the numbers here and the angles here to avoid having to round. But 10.770. So that's the magnitude of our force. That's how much force member BD is carrying. It came out positive. So our assumed direction for member BD is correct, or for force BD is correct. So to figure out whether that means tension or compression, let's compare the free body diagram of joint B to where the member is. The member is upper left of joint B. So the member is right in here. So it's pushing joint B away. And according to our drawing here, our decoder, that looks like compression. So when the joint is pushed away from the middle of the beam, when the joints are pushed away from each other, that's compression. That's a sign you're dealing with compression. So we can check the compression box for BD. And we can round here. Since we didn't really have to round anything else off, we can kind of go to our final answers here. We'll make those all 3 sig fig to meet the specification of the problem. This one, 10.8 in compression. So there we've got our table filled out. we can finish by drawing our force summary diagram. So that's just a copy, and generally as big as you can make it so that it's clear. The smaller you try to make it, the harder it's going to be to read. So we'll put in our reaction forces. We have 10 kips and 1 kip. We had 9 kips here. We had our applied loads. We had 10 kips and 5 kips and 3 kips. And label the members A, B, C, and D. And now just go through and translate what you've got on your table onto the drawing. So member AB carries 10.0 kips in tension. Member AD carries 1.00 kips in tension. Member BC carries 5.00 kips in compression. Member CD or BD carried 10.8 in compression. And member CD carries 10 in tension. So there's our force summary diagram. So that has everything that's going on in the truss, everything we've learned from solving our equilibrium equations. Now, looking at that, we can get a little bit of a better idea of trying to predict tension and compression, trying to get a feel for whether we've got something that's right or not. Over here, we'd expect compression to be going on because you've got that 5 kips pushing right down on C. If that member were all alone, it would be what we call a column, and we'd be pushing down on the top of it. That's putting that member into compression. We've got 9 kips pushing from down below, so that's helping to put it into compression. But notice that we get all the 5 kips here. We don't get the 9. That's because there's something else interacting at joint B. That 10.8 kips, the piece of that is in compression, that's pushing down and to the right. That happens to have a 4 kip downward component, which is what cancels out the 9 kips partially and ends up with 5 on each end. We look at the 10 kip force here. We've got 10 kips pulling to the right. Kind of makes sense. It puts this upper member into tension. But think about how this would move. If you pulled really, really hard at joint C, not only would this thing start to move, it's going to try to move to the right. The only thing keeping it from moving to the right is this cross member. This cross piece, as you're pulling to the right on the top, that cross piece is fighting back. It's creating compression. It goes into compression to help oppose this 10 kips of force because nothing else is there to do it. And in fact, the horizontal component of this 10.8 kips is 10 kips to the left. Now, this down here at B, this is a roller. And a roller doesn't handle sideways forces. So that roller is going to try to roll a little to the right. And as it does, it's going to put member AB into tension. It's going to stretch out member AB. So that roller allows the structure to move a little bit as we're pulling on it with this 10 kips of force. The compression that's created to keep the top in equilibrium has to be opposed somewhere else, and it's opposed down here at this roller. The roller moves to put member AB into tension. Now, that's how A ends up with its 10 kips of force on the support. That's where that force is resolved. So by looking at the internal picture of the truss, we can now see how that 10 kip force is getting down to where it was reacted at in the external problem. In the external problem, we figured out, well, it's got to be the pin supported A pulling to the left that opposes this. Well, how does that get there? Well, it pulls on CD, which pushes on BD, which pulls on AB, which gets it there. That's what I mean when I say that the external loads are translated down to or transferred down to the supports. So you can see a pretty clear example of how that happens in the truss. And notice that it costs more force than what was applied. When you've got cross members and such, those can often have higher loads than the applied loads. So you can't just say, well, the biggest weight I'm ever going to have on this is 10,000 pounds. So as long as everything can handle 10,000 pounds, I'm good. Doesn't work. You can have higher loads depending on the angles. The verticals here, why this is in tension is because as we're pulling here, the whole thing's trying to rotate too. We've got moment, and member AD has to be pulled down on by the support to keep it from rotating, and that puts member AD into tension. Essentially, member BD is pushing up too hard. Member BD is pushing up too hard in compression, so that 3 kips is partially counteracted, but we need a little bit more from the tension of member AD to put that part of the truss into equilibrium. So it's worth kind of staring at these for a little while and trying to figure out how would this work. And a really good visualization technique is to imagine it deforming. Imagine it changing shape. Imagine building this and watching it try to start to fall over. How is it going to move and what's going to fight it from moving? And that'll give you some idea of how things are in tension or compression. Any questions there?
Nope.
All right. So, like I said, there's a lot there, a lot to digest. It's probably worth going back and watching this to see how to work through it and try to work it through yourself and practice on it. Um, Wednesday night will be, I'll do another example problem, and then we'll be spending the rest of the time doing practice. Any questions there?
Nope.
All right. Well, then have a good night, and I will see you Wednesday evening.